Hello and welcome to Engineers Mindset Academy. So in today's class, we are going to be talking about analytic functions in Engineering Mathematics 5. Okay, so talking about analytic function, let's consider the given functions. Let f of z be equal to u plus iv. So this is actually a complex number. A complex number is a number which involves the real part and an imaginary part all together. So I have u plus iv. I here indicates imaginary. So which means u here stands for the real part of this complex number. Okay. Whereas v here stands for the imaginary part of the complex number. All right, imaginary part. So let f of z be equal to u plus iv, and okay, where z itself is actually also a complex number given as x plus I y. So this actually implies that z is a function of both x and y. Now, for a function to be analytic, that function must obey the Cauchy Riemann's equation. For a function to be analytic, it must satisfy or obey the Cauchy Riemann's equation. Okay, so what is the Cauchy Riemann's equation? We have that the partial derivative of u with respect to x must be equal to the partial derivative of v with respect to y, and the partial derivative of u with respect to y must be equal to minus the partial derivative of v with respect to x. So these two equations are called the Cauchy Riemann's equation. So whenever a function is given to you, any of the functions that satisfy this equation or this condition is said to be an analytic function. For instance, let's say we are given to investigate whether the function is analytic or not. Alright, so let's say we are given to investigate if this function is analytic or not. So let's pull it out. We have that f of z equals x squared plus I y squared, but not also forgetting that we stated earlier here that f of z is equal to u plus iv. So that simply implies that f of z is equal to u plus iv. Okay, so if f of z is u plus iv, all we need to do at this point is what? Compare the imaginary parts and the real parts. Compare imaginary parts and real parts. So compare imaginary and real parts. Okay, so given the two equations, of course, both of them stands for f of z. So if we compare the real parts, we have u standing for what? X squared. So this simply implies that u is equal to x squared. And if we compare the imaginary part is that part that carries the complex number I. So we have I here and we have I here. So comparing these two, it means that v is equal to what? Y all squared. So we have this condition set now. We need to now investigate if this function is analytic or not by satisfying the Cauchy Riemann's equation. So the first equation says differentiate u with respect to x, then differentiate v with respect to y. If both of them are equal, then we'll try the second equation and see. If they obey any of this equation, then the function is said to be analytic. All right. So from u equals x squared, differentiate u partially with respect to x, which means you're only differentiating the function that carries x. So if I differentiate u with respect to x, of course, this will give me 2x. Also, differentiate v partially with respect to y. So let's try this and see. Partial v, partial y also gave me what? 2y. Now, these two equations, we have that. Okay, keeping this aside, let's try the next condition. Next condition says differentiate u with respect to y and also differentiate v with respect to x. If I differentiate u, partial u all over partial y, this will obviously give me what? 0, because u is a function of x squared here, there's no y attached to it, and this is partial derivative. So it means I am to differentiate u only with respect to y. So that simply means since there's no y attached to this variable, partial u partial y becomes 0. And the next condition says differentiate v with respect to x. And here v is a function of y only. There's no x variable attached to it. So partial v partial y, partial v partial x gives me 0. So let's investigate the equation now and see. The first equation says partial u partial x must be equal to partial v partial x partial y. And if we look at this condition, partial u partial x gave me 2x. So I have, okay, let's put it over here. Partial u partial x from there gave me 2x. And again, partial v partial y from there, partial v partial y gave me 2y. So which means 2x is not equal to what? 2y. This simply means that partial u all over partial x is not equal to partial v all over partial y. First condition has been failed. Let's try the next condition. Next condition we had 0, okay, for partial u partial x, partial u partial y gave us 0. And again, we have partial u, we have partial v partial x to also be 0, but not minus 0. It has to be minus to the given variable. So since 0 is not equal to minus 0, obviously 0 is equal to minus 0, but then we are satisfying the equation. But since 0 is not equal to minus 0, it simply means that partial u all over partial y is not equal to minus partial v all over partial x. So this means that the function is not analytic. Alright, so since the equations after analyzing does not satisfy this condition, the Cauchy Riemann equation, it simply means that the function, the given function, which is x squared plus I y squared and f of z, okay, f of z equal to this is not analytic. This function is not analytic. After investigating using the Cauchy Riemann equation, the function is not analytic. Let's try a different example now and see. Alright, so let's consider this other question. It says check if f of z equals sine z is analytic or not. So the function f of z is equal sine z. So we have to investigate if this function is analytic or not. But before doing that, first of all, recall I said earlier that always we consider z to be equal to x plus I y. Always consider z to be equal to this, and you consider also f of z to be equal to u plus I v. So if z is equal to x plus iy, it means that we can write this equation. This simply implies that f of z is now equal to sine, in place of z, z is x plus I y. Okay, so we simply employ what we know in our trigonometry to this. Remember, if I have sine a plus b from trigonometry, this is actually what? Sine a cos b plus cos a sine b from trigonometry. If I have sine a plus b, then we can expand it to be this. So this simply means that this function f of z can also be expanded. I have sine x plus iy. This becomes what? Sine x cos I y, okay, plus now it becomes cos x sine I y. Okay, so I have this. Alright, so please, something is very, very interesting here for you to note. Note, please, note that whenever I find the cosine of an imaginary function cos iy, it gives me a hyperbolic cosine. So I have cos y. If I find the cosine of an imaginary function, it gives me a hyperbolic function. So cos iy simply gives me what? Cos y. Whereas if I find the sine of an imaginary function, it gives me an imaginary hyperbolic function of sine. Okay, so cos Iy is simply cos y, and sin Iy simply gives me an imaginary hyperbolic function of sine. So it becomes I shine. Okay, I shine y is a hyperbolic function, but then for sine it carries the imaginary function along with it, whereas cos buries the imaginary function and becomes a real function. So you have this. So if this is okay now, then it means that we can rewrite this equation to be what? F of z to now be equal to, I have sine x cos Iy. Recall cos Iy becomes what? Cos y. So this becomes sine x cos y plus, I have here cos x, then I have sine Iy. Sine Iy becomes what? I shine y. So this becomes times I shine y. So if I rearrange this equation, I will have that f of z is equal to sine x cos y plus I cos x sine y. I have this. So having this now, it means that I've been able to what? Write these two equations into what? Real part and imaginary part. The side that carries the I or the imaginary number or the complex number becomes the imaginary part, whereas the side without an imaginary number becomes what? The real part. So I can now recall that I said earlier, f of z always should be taken as what? U plus IV. So with this now, I can now compare what? The imaginary parts and the real parts. So comparing or compare real parts, real and imaginary parts. Okay, compare the real part and the imaginary parts given these two. So if you do that, it simply means that the real part here is u. U is equal to what? The whole real part on this equation, which is sine x cos y, and the imaginary part, which is now v. V is the imaginary part on this case, and it is equal to what? This. You have cos s sine y. So you have this. So we said that for a function to be analytic, it must satisfy or it must obey the Cauchy Riemann's equation. For a function to be analytic, it must obey the Cauchy Riemann's equation. What is the Cauchy Riemann's equation? Partial u all over partial x must be equal to partial v all over partial y. That's the first equation. And the second equation says partial u all over partial y must be equal to minus partial v all over partial x. So let's try to see if this condition will be satisfied. So we start from u. From u equals sine x cos y. From u equals sine x cos y. Therefore, differentiate u partially with respect to x. So which means you are not differentiating y. Y is held constant. You are only differentiating what? X. U with respect to x. So to do that, it means that this is cos y. So this whole is a function of y. We are keeping it constant and differentiating only what? Sine x. If I differentiate sine x, I'm going to have cos x. So this gives me cos x. Then put back your what? Cos y, because this is a function of y, so you're not touching it. It is partial derivative, so you're only differentiating with respect to x and keeping y as a constant. Okay. The next, we are trying to satisfy the first equation, please. So next thing to do is what? Differentiate v with respect to y. So from v is equal to cos s sine y. V is cos x sine y. So we differentiate v partially, partial v, partial y. Differentiate v with respect to y. So which means I will only differentiate terms with what? Y, keeping x as a constant. I have here cos x. So cos x will be treated as what? A constant. I'm not going to touch it because it does not contain y. I'm differentiating v partially only with respect to what? Y. So keeping cos x, if I differentiate sine y, I will obviously get cos y. If I differentiate sine y, I will have cos y. So this will give me what? Cos y. So let's compare the two equations. Notice that we have here partial u partial x give us cos x cos y, partial v partial y give us cos x cos y. So which means the first equation have been obeyed. Now we have that therefore partial u partial x equals partial v partial y, and it gave us cos x cos y. So keep this equation, equation 1, obeyed. This one has been obeyed. So let's try the second equation and see. Second equation simply says differentiate u with respect to y and differentiate v with respect to x. So let's find partial u partial y. So from u equals sine s cos y. Okay, I think I can do that over here. So from u equals sine s cos y, let's differentiate u with respect to y. Partial u partial y will give us, now we are keeping x as a constant, so you simply keep sine x, hold it as a constant since it doesn't contain y. Then we differentiate only cos y. Differentiating cos y, differentiate cos, you have sine y. If you differentiate cos y, you have sine y. Mind you, you have sine y. If you differentiate cos y, you have sine y. Also, from v is equal to cos x sine y. So you differentiate v, partial v, with respect to x. Differentiate v partially with respect to x. So we have to differentiate cos and not, this is cos x, the one that contains x, and not the one that contains y. So if you differentiate cos x, remember, you have minus sine x. If you differentiate cos x, you have minus sine x. So that gives you minus sine x. Now you keep sine y as a constant. Sine y. So let's take a look at this equation now. Let's try to compare. In the second equation simply says that partial u partial y must be equal to what? Minus partial v partial x. And if you take a look at these equations now, or these solutions obtained, partial u partial y is actually equal to what? Minus partial v partial x. Okay, both of them are equal and one is positive while the other is negative from Cauchy Riemann's second equation. So since partial u partial y is equal to minus partial v partial x, it means that the equation or the function, therefore f of z equals to sine z is analytic. Yes. Mm-hmm. Yes, it will give because yes, it's a hyperbolic function. When you differentiate cos for hyperbolic function, it gives you negative sign. Sorry, it gives you positive sign. But if you differentiate sine, the sign of the hyperbolic function gives you a negative cos. So the both of them takes the inverse of what they take in their normal state. Yes. All right. So please also take note when you differentiate the cos or the cos of a hyperbolic function, you have a positive sign or a positive sign for a hyperbolic function. And when you differentiate the sign of a hyperbolic function or the sign of a hyperbolic function, which is called sine, you have a negative hyperbolic function for cos. So the both of them actually take the opposite of what they assume in their normal states. For instance, if I differentiate cos, I will have minus sine. But if it was to be a hyperbolic cos, I will have plus sine or plus sine. But then if I differentiate sine, normally, if I differentiate sine, I will have positive cos. But if it was a hyperbolic sine, that is sine, I will have a negative cos. So both of them alternate when it comes to what? Hyperbolic functions. So just keep that in mind. But then, since the functions are equal and they satisfy the Cauchy Riemann's equation, it means that this function f of z equals sine z is analytic. Alright guys, so that's it on analytic function. I hope you find this video very helpful. In the next video, we are going to be starting a series on integration on a complex plane, still engineering mathematics 5. We are going to be starting integration on a complex plane. I hope you stay tuned, and of course, like this video, share to your friends, comment on the comment section, and of course, subscribe if you're new to the channel. I will see you in the next video. Thanks and cheers.